for everyone who is unaware, I mentioned that I wanted to do precomputed atmospheric scattering, and then Owen's actually one who actually did a whole bunch of research and understands this way better than I do. And I'm like, you should be presenting this. So I really appreciate Owen for stepping up and making slides and whatnot.
Yeah, I should specify that I'm very much not an expert on this. This is my results of kind of studying it over the weekend. I think I understand it pretty well, so I've tried to kind of distill that down here. I did leave out some of the kind of implementation details that I think are less important than just understanding the concepts, but I kind of near the end, I'll go over kind of what I skipped here. Yeah, so this is a paper by Eric Bruneton and Fabrice Neyret. I'm not sure how to pronounce that, but let's see. I'll kind of start with just some results of it to kind of get everyone interested in this. So here's kind of what kind of results you get. So for different times of day, you get different colored sky. For different altitudes, you can see how it affects the landscape at a distance. And it's really just kind of showing how the atmosphere affects the light that you see based on your position, altitude, angle. So just to kind of clarify what atmospheric scattering is, this is basically just saying that the light traveling through the atmosphere at every point along in the atmosphere some amount of that light will get scattered in a different direction than the way it was heading previously. So the light comes from the sun, hits the atmosphere, some of it will scatter a different direction, some of it will keep going the same direction, but some of it will go differently. And then each of those scattering results will also scatter into a different direction as well. So what we really want here is to figure out a way to find, given our viewpoint and where we're looking, how much light comes into our eye. And it could come from anywhere, right? It could have scattered 1,000,000 times before it got to our eye. It could have scattered once. It could have scattered no times and it came straight from the sun. So there's kind of two forms of scattering that we consider here. First one is Rayleigh scattering, and this is basically scattering that's caused by the actual air molecules in the atmosphere. So as the light travels through air specifically, it will be scattered. And this is kind of describing how that scattering works, how it behaves. So there's two coefficients that we multiply together to figure out the scattering. The first, the scattering coefficient. And that's basically saying that at a height h, how much of the light got scattered, just how much of it got scattered. It doesn't say anything about where it got scattered, just how much of it left the original direction. And then you also have the phase function, and this is where the direction comes in. This is saying that of that light that scattered, we know how proportionally how much got scattered, how much of that went in a specific direction. So in this case, mu, the argument here is basically the cosine of the angle. So if you want to know how much light went 90 degrees, then you would do cos 90 degrees as the input. And just kind of to demonstrate how these are laid out, this is going to pop up a lot. So these beta is the scattering coefficient, specifically beta superscript S for scattering. The R just implies Rayleigh, and the H is basically the height above the ground. So that's one of your inputs. It's basically your altitude within the atmosphere. And then it also takes in wavelength. So this is the actual light that's being scattered. So since we're doing computer graphics on a computer, this is actually just going to be represented as a vector. So RGB, 3 different wavelengths. And similar to the phase function, we just mark it as the Rayleigh phase function specifically. And we use mu instead of the angle. We always deal with the cosine of the angle. My guess is that's basically just because it's easier to do all the math we're going to do on the cosine of it, because it's nicely between -1 and 1 rather than dealing with the angle directly. But so here is what that scattering coefficient actually is. Here's how you calculate it. It's somewhat scary looking, but basically it's there's like this n is the index of reflection of the air. The big N is the density of the air at sea level. But how they actually use it in this paper is basically just ignore that big scary bit and use a constant for that. This is something that you would want to not use a constant if you're wanting to model like different atmospheres that have different composition of air in them, different heights or something. But when this paper is specifically talking about the Earth, they just kind of set it to a constant. You can see it's a vec3 again, because this is dependent on the wavelength. So there's 3 different values, one for each of the red, green, and blue light. One thing to notice is that the blue light has a lot higher constant here than the other ones. And this is basically saying blue light scatters more than other colors of light. But this is where the sky being blue comes from. This is why that's the case. It's because as light travels through the atmosphere, the blue light gets scattered more. So in any given direction you look, there's a lot of blue light traveling through there because it's been scattered around. And then the other important part is the E, so the exponential term here. This is where you use the height, and specifically you divide the height first by a constant, and this is basically just a way to scale the exponential function to represent how the different, so like the air has a specific kind of distribution throughout the atmosphere. It's not uniformly dense, and this is kind of just scaling it so that it fits within how the air actually works in the atmosphere. You can basically just treat it as a constant in this case. And you'll see that this changed the function to be just a function of height. So that's very useful. We don't have to put the light in because we're dealing with just constant light on the computer. So the phase function, here's the Rayleigh phase function. It's pretty straightforward. It's just function of the cosine of the angle, and you just apply these calculations to it. So the other form of scattering is Mie scattering, and this is the scattering that's caused by aerosols in the atmosphere. So from my understanding, that's things like ozone particles. You start getting into the physics side of things, and that's where I don't know much about it, but basically there's another form of scattering. So very similar coefficients here, but notice that we use an M to determine its Mie scattering. But it's, yeah, the same kinds of functions. Here's the simplified version of the Mie scattering coefficient. Just like the other one, there is a real function that you can use if you have a different atmosphere, but for these purposes, these constants work well. And then the difference here is that all 3 wavelengths have the same value, and this basically just means that Mie scattering, all the light gets scattered uniformly, so there's no color shifting. This happens. And then it's also got the exponential term, and the Mie scattering with the aerosols has a lower, like you divide it by 1.2 kilometers instead of 8, but I don't think that's really important. Just know it's scaling the density, basically. The Mie scattering phase functions a bit more complicated, but they don't get into what G represents. I think this is kind of, again, where it veers into the more physics territory, but in the paper, they just set G equals 0.76, and that makes this function kind of less scary to compute. So the other important coefficient to know is the extinction coefficient. So this is basically saying if the scattering coefficient is at a point how much light gets scattered away, the extinction coefficient is how much light gets lost. So for Rayleigh scattering, no additional light gets lost. It's just however much light scattered away, that's how much you lost. For Mie scattering, however, I think some of those aerosols can also absorb light. So you have to divide the scattering by 0.9, which you'll notice since the divisor is less than 1, then this actually increases a bit. So there's a little bit extra light lost than just what was scattered away. Some of it gets absorbed as well. And we have the superscript E there just to note that this is the extinction coefficient. Okay, I see in the chat that G is for forward scattering, G is positive, and G is less than 0, it's backward scattering. Okay, that's interesting. I would like to learn more about that. Okay, so just a little definition here. This is the lighting equation, where it's just basically saying all the light coming in to a point from a direction, and S here is basically the direction towards the sun. So all the light is calculated with this function of 3 variables. This is the thing that we are wanting to find. Like, this is the hard equation that we don't know, because this is saying at any given point in the atmosphere, looking in any given direction, how much light is coming in from that direction. And so this is light that came straight from the sun, if you're looking at the sun. This is light that came from the sun, went into the atmosphere, bounced once, and then went into your view. This is light that bounced twice, 3 times, infinite amount of times. So this is what we're trying to approximate and figure out with this algorithm. So in order to figure out how to calculate that light equation, there are a few intermediate things we need to know. So one of those is the transmittance. So this is basically, if you're looking in a direction towards an endpoint, because if you're looking down, the endpoint is going to be on the ground somewhere. If you're looking up, the endpoint will be on the edge of the atmosphere, because scattering only happens within the atmosphere. So there's always going to be an endpoint from where you're looking at. And this is saying that of the light that left that endpoint towards you, how much of it actually reached you. So along that path, some of it's going to get absorbed, some of it's going to get scattered away. You're going to lose some of it. And this is basically telling you how much reached you. Second, we need to know the ground reflection. So this is basically saying at a point on the ground, how much light from every direction hit that point and then reflected away. And this paper assumes the ground is a Lambertian surface, so it reflects evenly in every direction. So you don't need to know the specific angle you're looking at the ground in. It's just how much light is coming into the ground and then reflecting away. So this is going to be dependent on the surface properties, like whether it's super rough or something, and also depend on knowing how much light is entering that spot. Third, we want to know how much light is scattered into a point. So this is saying that for any point within the atmosphere, how much light, in the sphere of directions around it, every single direction, how much light is getting scattered into that point. So yeah, it's just all the light entering a point. And then specifically leaving that point towards your viewpoint. So all the light coming in and then getting scattered towards you. And this is at a specific point. And then the kind of extension of that is the final image here, which is how much light was scattered in along a view. So this is basically saying, given your view ray towards the ground, towards the edge of the atmosphere, for every point along that ray, figure out how much light scattered into that point towards you. So this is basically just kind of the summation of the previous one, which is the scattered light at a point. So just go over a little bit more. So here's the transmittance, which, reminder, it's just along a ray, how much of the light actually reached you and didn't get scattered away. This is the way to calculate that. It's an exponential of the integral from your starting position to your end position of the ray. For every point along there, basically sum up the how much the extinction factor of Rayleigh scattering at that point along the ray, and the extinction factor of the Mie scattering at that point. And yeah, and then you get that sum, do an exponential of it. That gives you your transmittance. So the important thing here is that there's not really any unknown variables here, besides your input, but those are just 2 positions. So that is fairly easy to pre-compute online if you know which positions you want to test ahead of time. You don't need any runtime information to figure this out. So it's quite easy to pre-compute. So here's the kind of more formal definition of that ground reflectance. So this is how much light came into a point and then reflected away. So the integral part here is really just over the hemisphere around the point. For every direction on that hemisphere, figure out how much light came in. The omega dot product normal here is just saying it's a cosine foreshortening. That's pretty standard in rendering. And the first kind of coefficient there is really just the reflectance of the ground, and divided by pi for like a line version reflectance. So that is just how much light reflected off of a point. When we're actually like rendering with this, we want to know how much of it came and got to us. So we need to scale that by the transmittance, because as the light reflected off the point towards us, it still had to travel through the air before it reaches us, and some of it will be lost along that distance. So that's what our transmittance was telling us. Between the points, how much is lost. So if we want to know how much is reflected to us, we need to scale it first. So here's how we calculate how much scattered light into a point in space. It's fairly simple. It's just integrate over the sphere around that point. For every direction along that sphere, figure out how much light came in that way. And then remember, this is scattering out towards our viewpoint. So we need to use our Rayleigh and me scattering terms to scale that light to figure out how much actually came towards us. So you can see it's the product of the scattering coefficient with the phase function for the angle heading towards us. And then the kind of extension of that is how much was scattered in towards our view along the whole ray. So we can integrate over the ray, where we figure out how much light was scattered in at each point, which is what we just saw. And then again, that light, once it's scattered towards us, still has to travel a lot through the atmosphere to get to us. So some of it's going to be lost. So we need to multiply by the transmittance. So you might have noticed that I was told you these are used to calculate this lighting equation, which is, how much light is coming in from a direction, but most of those equations also used that function. So how do we actually, how do we resolve that? So it's useful to look at what the lighting equation actually is. And as I described it earlier, it's the direct lighting from the sun. It's the light that's scattered once on the way here. It's the light scattered twice. And this can be represented as a sum of those terms. So the subscript on L is basically how many times it's scattered on the way. So the real value of this L function is going to be at the infinite sum, right, of all possible amounts of scattering. An important thing, though, is that as you add more terms of this, you get very diminishing returns. And after a certain point, it's not very easy to tell what actually changed. So we don't need to have every term to get a decent approximation. And we can use the previous terms to calculate the next ones, which is how we get past this issue of the self-referential. You need all these scattering reflectance things to calculate L, but you also need L to calculate those. We can build it up from simpler models of scattering. So we can start with direct lighting, which is light coming just straight from the sun, not being scattered at all. Use that to come up with well, don't need it for transmittance, but come up with the reflected light, the in-scattered light. Use those to then calculate the next version of L with more scattering, and so on and so forth. I'll get into that a bit more here though. So first, how do we get the first term of the light with no scattering at all? This is just a pretty standard graphics thing where it's super easy to calculate runtime. It's really just, if you're looking at the sun, then it's equal to how much radiance is coming from the sun. If you're not looking at the sun, it's nothing, because if you're not looking at the sun, then it can't directly travel towards your view. So this is super easy to figure out on the fly. The next part is, how do you calculate the light that is scattered once before arriving? So this is basically all the light that has been directly towards you or scattered once on its way to you. And this can be calculated using the direct light plus all the light that came from the ground, like was reflected off the ground towards you, and how much light was scattered along your view ray, but with only the direct light. So this is saying this kind of a bracket notation here next to this terms is basically saying that equation wanted the full lighting function to figure it out, but for now just use the direct lighting for that instead. Use a simpler version of light. So this is saying all of the direct light plus all of the light reflected off the ground towards you, but only the direct light that hit the ground, plus only the direct light that got scattered towards you. And this will become a little bit more clear when I show the actual computation of this, but you can see, you'll be able to see later that these equations get a lot simpler in this case. You can make some assumptions and make it so you don't need to fully calculate these integrals and stuff. But these equations here I'm showing are really just the ones I showed previously that are substituted for the actual values here. So they look scary, there's a ton going on, but it is just those same basic concepts. So here's basically another way of saying that, that you can add up different scattering terms of light. So see that the real function of L, all the light coming in, is the sum of just the direct light coming in, plus the light that got scattered once, reflected off the ground and just in the air. And then you take that term that you calculated and you can use that as the lighting equation for your next terms. You can plug that into your ground reflection function. You can plug that into the scattering in along array function as your lighting. And as you do this, you can get more and more accurate results. Essentially, it's basically dynamic programming, right? Like we are building it up from the ground up. We're figuring out this really complicated function can be found with results of adding up simpler equations, and we just save them and memoize it and add it up together and build it up to the final result.
There's a question in the chat from David. Seems like a decent.
Yeah, okay, so figuring out how to make the light actually physically accurate. That's a good question. That's interesting. I guess if you're gonna go full physically accurate, then you would be using, like, I'm not sure I forget what the actual units of radiance are, but you would be using like the measured radiance of the sun, right? So
right.
If everything else in your system is using the correct units, theoretically you could just plug in the real value.
Well, I mean, when it comes out on the other side, I noticed that it was just kind of when you do something. I mean, let's say their radiance seems like the term varied when I'd go from location to location, and you try to grab out, the amount of watts per meter the sun puts out. It didn't quite work out, and then that didn't quite work out to how that translates to the human eye actually recording that information. It all became really complicated very quickly, and I wondered if, seeing as the paper kind of glossed over and then here is your L nod, just go grab the value of the sun. I'm like, wait, where does anybody know what this magic number is?
Yeah, that's a great point. That's something I wish I knew more about, but unfortunately I really can't help you there.
So I'm stuck with having to guess and leave it as guesses for the rest of time.
I think so.
Thank you, though.
No worries. Yeah.
I mean, one could imagine that you could recreate the Sun-Earth system and try to see if that looks somewhat correct.
Yeah, I think that point of like knowing the exposure when it gets like to your actual eye and stuff, that's definitely when it would get really tricky.
Yeah.
Okay, so basically the key to this is building it up from lower terms, and the key for it to actually run in real time is that we need to compute a lot of this offline. So we need to figure out what of these equations can we factor out from relying on our runtime information, and how much of it can we just compute into some lookup textures and just grab it when we're actually trying to render and quickly figure out the results. So first we'll start with the transmittance, and just a reminder, this is from a start point and the end point, how much of the light along that ray actually reached you. This is fairly easy to compute offline because it doesn't really require any information about your scene except the atmosphere, and that's probably going to stay pretty constant within your scene, so it's pretty easy to compute offline. However, transmittance is a function of 2 points. Point in this case is 3, like an X, Y, and Z coordinate. So that's 6 basically values for an input. And that's going to be a big lookup table. If you have like a 6D table, that's not going to be very good. So the key is to kind of simplify the scenario here. This is something the paper goes into a lot of detail about, but essentially we're going to assume that this planet is a perfect sphere. This isn't true, and the paper goes into a lot of detail about how you can compute this stuff using that assumption and then do a few things to it afterwards to make it correct for your actual shape of your planet. I'm not going to get into how that happens. It's described in the paper pretty well. I think it just kind of, for the purposes of this, just kind of complicates it a little. So I'm just going to stick with assume the planet is perfectly sphere. So in this case, since it's a perfect sphere, your actual position within the atmosphere doesn't really matter because you're on top of the sphere. So in every direction, it's pretty symmetrical. So at the end of the day, all that really matters for your position is your altitude, because you could move your point at the same altitude around the sphere and you're still just over a sphere. So now that's one of your starting point is now just a single number, your altitude. But now you need to figure out your endpoint. And that is very easily determined by which direction you're looking, right? It's just a raycast from your point, add an angle, figure out where it hit. So all you need to store is that angle. And because we're dealing with that sphere and all we need to know is the height, that's really just a single angle, which is the angle from like straight up on the planet down to the ground. You don't need like a 2-dimensional angle or anything like that because of the symmetry of the sphere that you're on top of. So we can represent this lookup table as with only 2 inputs, which is your height and your view angle. So that's what I say here at the bottom. They call your height R for, I guess, like radius, I guess, and your view angle is mu. And this is, again, the cosine of your view angle. We basically almost never use the angles directly. It's the cosine of it. So here's kind of a demonstration of that. It'll be the same. You can do it in 2D because of the symmetry of the sphere you're on. So the angle you're dealing with is from straight up between the angle down. And remember that this endpoint can also be on the edge of the atmosphere too, if you're looking up. So if you go through and for every value R from every altitude between sea level and the top of the atmosphere, at each of those points for every angle up and down, you can build up this texture. The paper doesn't, there's a lot of detail into how you store this because it's not just a direct, you know, like on the x-axis is mu. There's a lot of consideration for maintaining precision with this because the angle, the precision of the angle matters a decent amount because, for example, this table is only 256 pixels wide. That's not that many different discrete angles, 256 angles. So they do a fancy mapping so that more precision is saved for, I think, near the horizon, basically where more detail of the angle actually matters more. But that's kind of just an implementation detail that you don't need to worry about. So, okay, so we have the transmittance now. Now we want to try to pre-compute the ground reflection. So a reminder, here's what this I equation at the top is basically how much light enters a spot on the ground and is reflected away. And then the R equation is specifically for your viewpoint, how much of that reflected light gets towards you. So in the R equation, you see that's got transmittance. Well, we just pre-computed that, so we have that. Now we just need the I equation. Specifically though, the reflectance of the ground, that is something that we're probably only going to know at runtime because it's going to rely on the actual properties of the point we're looking at. So we will we'll pull that out of I and just make sure we apply that at runtime. So all we actually want to calculate offline is this epsilon, I guess, equation here, where it's basically just the integral part of the I. And notice that if your viewpoint, the end of your view is not on the ground, then this is just equal to 0 because there's no ground reflectance coming from the edge of the atmosphere because it's not the ground. So just like the transmittance one, we can represent our position as just the height because we're still assuming it's a spherical planet. And we can represent the sun direction by just a single angle as well, which is just how, you know, from your height, how much up or down is the sun. Again, because it's a spherical scenario here. So if you just kind of plug in values and for this L that is the unknown, we're just going to use, we're going to be building this up. So at first it'll just be the direct light, which is easily known. Then it'll just be the single scattered light. Then it'll be the double scattered light. And we'll compute each step of this along the way. So this is what the final result after all of that stepping will look kind of like. It's a 2D texture, you get your sun angle, your altitude. You can just look up the value of this epsilon, but remember that this is just this is the reflectance at the point that hasn't been scaled by the actual properties of the ground. So at runtime, we'll have to apply that. And the last table is the in-scatter. That's that S equation. This is kind of the meat of it. This is the really hard one. It's basically saying for given a view angle, how much light entered that ray along it. So for each point along the ray, how much light gets scattered into that point towards you. These are just the equations again. So for each point, we'll have to integrate over the sphere around it, figure out how much light's coming in. So we're gonna need lookup tables for both of these because we can't just factor away the how much light got scattered into each point. We're gonna need to know that. We have to calculate that. But the final lookup texture that we're gonna need at runtime is just this S1, how much light scattered in along the ray. The J one is really just while we're building up these tables, we're going to need to have that information. So some of the other ones, we can simplify how many inputs these lookups have by using that spherical assumption. So we just need to store your point's height, your angle, the angle of the sun, and then also the angle between your view and the sun. That's going to affect things as well. So that's actually a 4D lookup table. They still stored it in a 3D texture by just, you can kind of see in this image at the bottom here, they just kind of pack the 4th dimension into the X dimension as well. So more just implementation details. So here's the actual algorithm, how to build up these tables, how to calculate these things so that you can calculate the final real approximation of your lighting equation. So this is complicated looking, so I'll go through it step by step. First, pre-compute the transmittance. Went over that. It's pretty easy, no unknowns, just have to create that. Next, you have to compute the ground irradiance lookup texture. So that is how much light is entering each spot in the ground. Remember, this is no longer the reflectance one because we took out the ground reflectance property, which we will add back in at runtime. This is just how much light's entering the point. It's easy to compute this because you just need to know the direction of the sun. That's in your scene, it's going to be somewhat constant. If you move your sun, you're going to have to recompute all these tables, but it's not so bad. So because this table requires the lighting equation to figure out how much light's entering, we're going to have to build it up step by step as well. So for each step, we're going to have a table that is delta E, which is basically just how much it changed from the last iteration, how much of the, if you previously calculated how much direct lighting, and then now you're doing the single scattering, this delta E will be just the single scattering part, not the direct lighting as well. And then we'll kind of just sum it up over time into the actual E table, which is the real value of it for every scattering. Okay, so to start off the algorithm, we need to kind of seed it with some information at first. So we first calculate it using the direct light as the lighting equation. So you can see it's that. Oh, sorry, this is the in scatter. We'll move on for the ground irradiance one. So for the in scattering one, we also want to just compute it just for the in scatter, the direct light at first, because that's all we know right off the bat. So we've got this bracket equate the syntax again, where we're basically saying instead of a lighting equation, use direct lighting as your equation. So you can see that all of those L in these equations has been replaced with L0. And remember, L0 direct light, it's trivial to determine because it's just if you're looking at the light or not. So this is, the value of this is going to be how much light is scattered into your view, but that light was originally straight from the sun, so scattered once. So using that, you can kind of simplify this a bit. So the light is still being scattered into our view, but we know where that light came from, which is the sun. So at each point along our array, we no longer have to integrate over the whole sphere to figure out every direction. We can just look at the sun and see the direction. We don't have to calculate this integral. So I've this written out equation near the bottom is basically with that assumption. The in scatter light at each point is now just a summation of these two terms. And those are all known at this point, so we can compute that. And then for the total scattered light along the whole array, we will still have to integrate that, but it's going to be integrating these equations that we now know the answer to. So just like E, we're storing the extra scattered information into a delta S table. We want to know we want to isolate the newly added information so we don't accidentally add too much when we're computing the other parts. So the final scattering table, which is S at the beginning, we'll just set it to the delta S, adding with the single scattering in it. And then here's kind of the iterative loop of this. Here's what we build up these tables with more and more information. And orders is basically how much scattering do you want to compute? Do you want to do single scattering, double scattering, triple scattering, as many times as you want? The more you add, the more accurate you'll get, but I think typically they don't really go past 3 because it's just not, doesn't really add that much after that. So this kind of scary part is really just saying, use the previous iterations intermediate values to represent the lighting function that you're going to use in these equations. So you can see this, these are the same here because it's just saying the previous iteration's light. So here's a breakdown of that one line of how we compute the delta in scattered to a single point table. This first part of that previous iterations information is the transmittance. So how much of it reached that point, the reflectance of the ground irradiance, add in the in-scattered light. And remember, these will just be at first, those will be just the direct light. Next time they'll be like just the single scattered light, and so on. But this time, when we're calculating the in-scattered at a point, we can't make any assumptions now where the light came from. We do have to integrate over the whole sphere, but we can use the previous iterations information as a lighting equation, so we still know all of the terms. It's just a matter of calculating it. Same for the delta E. This is the ground irradiance. So one thing is that using the previous iterations information includes the light reflected off the ground, but that's not going to matter in this case. That won't be a contribution because we're looking at a point on the ground. So the light can't bounce off the ground and then hit the ground because we're on a sphere. It can scatter and then hit the ground, but we're not talking about that here. We're just saying just the previous iteration scattering amounts. So we can't, we know that it traveled in a straight line off the ground, so it can't hit the ground again. So we can just ignore that term and just use the in-scattered light. And here I just highlighted that this in-scattered light is replacing the L here, which is replacing the lighting function. So we can just look this up. We don't need to calculate the light here because we can just use the previous table's information. So we do the same with the delta S. This is in scattered light along the ray. We just use the previous iterations table to look up the value. We don't need to calculate from scratch for the light equation. We still have to calculate the integral though. And yeah, so at the end of each iteration, we update the master table of all of the irradiance. We just add on the newly calculated stuff. All of the in-scattered light, we just add in the previous, what we just calculated. And we update these master tables with this information. So we do that for 3 iterations or so. Now those tables are getting more and more accurate. Now we can just use them to solve these equations at runtime. So how we render with this information is when we're rendering a pixel, we figure out all of our texture lookup parameters, such as like our height above the ground, our view angle, where the sun is, and we just plug those into these texture lookups to calculate what the approximation of the lighting equation is. So reminder, the lighting equation is approximated by direct lighting plus the ground irradiance times the surface material information, reflectance information, which we left out. Here's what we put it back in. And then we have to scale it by the transmittance between us and the point we're looking at, because it has to travel to us. Some of it will get lost. And then we also add in this in-scattered light along that ray, the light that was added to that ray by scattering in from elsewhere. And yes, this question, so the master tables are all part of the computation. Yes, so back to here, you say for each iteration, we calculate the delta table, which is how much we're adding on to that master table. And then we update the master table with that delta. And the reason why we separate these out is because we only want to calculate the new value of like in scattered light, ground irradiance, using just the delta of the previous iteration, because we're adding on to it every time. So if we were adding on the master table, it'd be like direct light plus single scatter plus direct light plus single scatter plus double scatter. So we'd be overcounting a lot. So we only want to add in the new term. So we need to keep the contribution of just the previous iteration, but we also want to update the master table. Hopefully that makes sense. So yeah, so this basically, we can use these lookup textures to represent the lighting equation as summation and product of those terms. And then basically what we have like essentially it's global illumination, like we know the light coming in, but it's global illumination that's only the light that came from the sun. So basically while you're rendering, if you want to know the light hitting a point, you can just use this lighting equation we've calculated here. If you have like other lights in your scene, I guess that won't be part of this, so you'll have to add on those separately. So this is just kind of like the diffuse lighting coming in pretty much. Okay, so I'll get into a bit of what I skipped here. There's a lot in this paper. This is basically the part where they talk about how we pretended the Earth was a perfect sphere, but it's not. So they have a bunch of information about how you get the real value from your spherical assumption calculations. Essentially, instead of placing your endpoint on the ground, you place it on the edge of the shadow. Instead, you only integrate along the point up until where it's shadowed. You have to like do something like shadow volumes to figure out where that shadow boundary is. But that's basically it. It's a little bit more complicated, but I got into this a little bit, but how you actually translate the text, like the lookup table inputs to texture coordinates, they get pretty complicated with that because they want to preserve precision for the important parts. For example, the angle, it's really mostly the angle. The angle can, the different angles for like your view angle, the sun angle can really affect the results pretty drastically. So you want that to have a lot of precision around the important angles, so that they have some more complicated mappings to make that happen. This in scattering table, which is the light scattering in along your ray. This, again, the phase part of the scattering affects this a lot, and that requires some pretty precise numbers. So they actually, in the real implementation, they decompose this table into two parts. One is the Rayleigh part, one is the me part, and they remove the phase function from it. They don't store that in the lookup table. So when you are at runtime, when you're looking at this value, you actually have to get the two values of the Rayleigh and the me, apply the phase function at runtime, and then put it back together to get the real value. It's kind of overcomplicated for just this presentation, but that's pretty important if you want to actually create these textures. Yeah, basically, yeah, again, like this, they go into a lot of detail of how to get the real height of the planet represented. A lot of it can be represented exactly. Some of it's an approximation, but you can read the paper to get more details on that. And here's some here's a link to the paper. The author, Eric Bruneton, also re-implemented it pretty recently. He's got a very fancy code base that you can look at. He added a ton of documentation, so it's pretty easy to read. It's still quite complicated, but I recommend checking that out if you want. And then also somebody made their master's thesis on implementing this in a deferred render. And that's where I grabbed a bunch of the screenshots of this, of the effects of it. So I recommend checking that out as well. And yeah, that's it. Thank you. Anyone have any questions or anything they want me to go over?
So just one thing. So I found that, so when you were explaining the, you know, the fact that you got the series, right? And you kept adding the L's to each other, right? With 0, 1, 2, 3. I noticed that that was really similar to the rendering equation and how that basically applies 1-to-1 with how you could do that. That I'm not wrong for thinking that, right? That's
it.
can
Yeah,
see it
it
the
really is
same.
the rendering equation. It's like that L is really just the light coming in at a certain angle. So that there really just is the rendering equation. This is just an approximation of it for specifically the environment in the atmosphere with all the light scattering around.
I wonder if you could like claim that this is a, what's it called? That this is like a subset of it. Like you can with like the different like weighted ray tracing and everything.
Yeah, I guess, yeah, it is a subset. It's the amount, it's the lighting equation that's specific to just the light added from sunlight bouncing on the atmosphere. So yeah, it's skipping all of the like more details of like point lights, it's skipping all that. I guess like specular reflections, I guess it's skipping that. So yeah, I guess you could say it's like a subset of that.
Did you want me to stream my build of it? Did you get it building?
No, I never did. Yeah, that'd be great if you could show that.
Okay.
Stop sharing.
We were talking about it last night and plinking around in RenderDoc. What's fun is we saw some massive render bugs last night that running it here don't have. So the basic scene here is a little sphere with a shadow thingy on it.
Yeah, I think you're
If you
showing
zoom
the wrong
out
screen.
Yeah, I think you're
further
showing
and
the
further,
wrong
you can
screen.
see the atmosphere. There's the sun in the distance.
Charles, I think you're sharing the wrong screen.
Oh,
You can't-
really?
Yeah.
Every time new share, just there we go. So let me zoom in real far, get the little sphere just to see what it looks like on the surface. And as we zoom out, it gets fuzzier and fuzzier. You can see the sphere barely. Is that sphere too small to be seen by the? But
We can see it fine.
Yeah, it's fine. We can see it.
I don't know. Just making sure it can be seen. And you can see we're in the atmosphere right now, as you can see with the gradient, but here we've exited it. And so all the light rays we're seeing through here are going to be entering and exiting the atmosphere. So that's a cool effect. And I'm going to pull down, and this looks like Google Earth if you've ever toyed around with that.
Google Earth after global warming.
Yeah, the sun is very plain, but you don't need a very strong sun to get some very nice effects. It's a whole bunch of presets you can flick through, some nice sunset vistas. You can see how the orange scattering or the orange and redness come into play. Oh, did he? Oh, that's cool. It is implemented in Google Earth. No wonder it looks so similar. One weird thing, can you see the line going through the sphere here?
No.
Okay, maybe the compression has eaten it, but I'm still seeing an artifact where this sphere is being rendered like after the planet is. And so there's some weird artifacts, and I was seeing a lot more of it last night, but something as funky is going on, and I don't know enough to how to fix it.
This is on the CPU, right?
No, this is GPU.
Oh.
This is rendering with like blood or something, so it's It's not terribly advanced, but it's OpenGL 3.3, so it's advanced
Oh,
enough.
okay.
That's worth mentioning too, that all those pre-computations were all done on the GPU as well. Like they
Yeah.
do it all. They did it all as like a pixel shaders on a quad, but
Like,
I'm in the middle of trying to implement it, and it seems easier just to do it with compute shaders. But yeah, it's all
Yeah.
very easily parallelizable.
the reason I shared my screen instead of an application is because we got RenderDoc working, and it's relatively illustrative to see the individual steps. So this is a frame zero capture, and it's a bit hard to figure out which each thing is if you're not familiar with the algorithm, which is why Owen here can commentate. But like you have your all of these things, save for this last one, is the pre-computation going on. And so because it's a 3D texture that's treated as 4D, there's a whole bunch of slices. And see where, and like this is like the 12th or whatever thing. And so only slices 0 through 10 have been computed. And if we go to slice 11, it hasn't been computed, and then the next draw call computes that one. So as you go through all of them, this is the output over time, and you can see that this is like the base scattering. Is that right? The amount of scattering you get from the 0th iteration.
I think so. Yeah, I find it.
Yeah,
to
I don't want to
interpret
speak
these,
authoritatively. It's an iterative algorithm. So after you get the initial setup, you keep doing passes. We were looking at all of these things, and we were very confused because it's just black the entire time. What we didn't realize was until later on that the scale that these things operate as very low. Okay, or not that. Oh, yes. So we had to boost the gain on it, so to speak, to be able to see the actual slices values. And so you can see by the very end, we're dealing with very small numbers. And can you even see the blue here across the surface? I need to boost that more. So that's yeah. What the comment really is just that there is a whole lot of precision to be thinking about here that I did not realize was necessary until I started seeing all these very small numbers being spit out by the algorithm. And it basically repeats that 3 times. And this is the final something rather.
It's a great tip from Jakers to hit that little magic wand button next to the scale.
There's a magic wand button?
To the right of this.
The right of the slider.
Yeah.
Okay. I can barely tell that's a magic wand.
Fair enough.
So that's super useful. That's very useful. Thank you for letting us know. Of course, the magic wand for the first slice, which is at a different altitude, was it? Did we think? Trying to figure out which slice corresponds to which view angle and altitude is a black art, so I'm not going to just presuppose, but the range is, the visual range goes from absolutely minuscule. I mean, if I right click a pixel, it's down at the bottom of the screen is the magnitude, and it's a very small number. Versus the very thing here, which is not that much smaller, but it is still a small number, or not that much bigger, I mean. The only thing that we can't show is the actual rendering of the scene. For whatever reason, it will not capture those draw calls. So the only draw call we get for the rendering of the scene is this one, and we believe it's missing like the capture is buggy somehow. Because the only draw calls after this are to draw the GUI, which is a whole lot of text being drawn. So that's unfortunate because I really wanted to see how those shaders work. But, oh well.
Yeah, overall, it's a very impressive effect.
Oh
Yeah. So is it running like smoother for you, or is that just a bit slow?
yeah. This is running 60 hertz, no problem. So it's very smooth for me.
Oh, okay. I
That's
think it's a
just
screen
the
share then.
Zoom.
Yeah.
It's sharing options. No, I can't. Yeah, no, that's just going to be Zoom being zoomy about video screens. So the sun is not in the sky, but we're still getting a lovely scattered vista, which just looks divine.
Shadow of the Earth on the other side. When you are closed and you see on the other direction, you can see the shadow of the Earth directly on the sky.
Oh,
When you are closer here,
right.
in front of you, that is a shadow of the planet.
Yeah,
That's cool.
yeah, you're right. That dark zone
And
there.
it's an effect you can see in real life, so that works.
You
That's really
can.
cool.
That is, yeah, you get down close to the level of the sphere and it shows up, that blackness. That's cool. Now we just need like a starry night drop, then that would look even cooler.
So I'm wondering if this algorithm, because I'm doing like voxel based stuff, so I'm wondering if this algorithm could be implemented for voxel, like a flat road. And for the
Yes.
flat earthers too. Just
So all the I guess you can treat it differently when you're actually calculating it versus rendering. So you can figure out what the characteristics of the planet would be as if it were round, and then use those like altitude values in all your pre-calculations. And then I guess just make sure when you're rendering that, even if it's flat, you get the right altitude, which you might kind of fudge a bit. But you can still use this lighting, all these values as if you're on a circular or spherical planet while you're just in your voxel environment.
I just noticed the banding going on here. I wonder if that's just you need to like triple or quadruple the size of your four-dimensional table to get rid of.
Yeah, I didn't actually mention that, but it's worth mentioning in the original paper, like these tables are quite small too. I imagine you could get pretty good results with making them bigger, but like the transmittant one is only 64 by 256. Like it's pretty small.
I did some back of the napkin math and I found like one of the 4D tables to only be about a megabyte in size after pre-computing. And that's for everything, which is pretty good for a 4D table.
And it's worth remembering that this paper came out in 2008, so the hardware was quite a lot more limited back then. Yeah, and then a lot of the fancy mappings they did to preserve precision at near the correct, like the important angles. I think that's really where they make these small textures work well. So, and yeah, like Jake said, the cache, it's very cache friendly.